Hello and welcome to the Terran Space Academy, where we help prepare you for a bright future in the space industry. Please don't forget to like and subscribe, and help us out on Patreon if you can. We appreciate you. We love ion propulsion systems, firmly believing that they are the future of efficient spaceflight for the next century, or at least until we can get fusion worked out. Blue Origin recently received a contract to produce a nuclear propulsion system. Don't ask me why. This would be a fission reactor producing electricity and heat. Fission, as you know, is very different from fusion. Fission reactors use neutrons like bullets to blast apart large atoms, like uranium and plutonium, into smaller atoms. This reaction gives off heat, which can be used to generate electricity through a turbine system or directly through a thermovoltaic cell. This heat can be used for spacecraft propulsion. For a given temperature, all gas particles have the same average kinetic energy. Therefore, the smallest mass particles will have the highest average velocity. A higher exhaust velocity at the end of your nozzle means a higher efficiency for your rocket engine. Thus, at the maximum temperature your engine can survive, for a thermal rocket engine, whether the heat source is chemical combustion or nuclear reaction, there is no better propellant than liquid hydrogen. Liquid hydrogen can also be pumped around your engine and nozzle to keep them from melting. Notice I did not say combustion chamber. There is no combustion in a fission-based nuclear thermal rocket engine. The liquid hydrogen is pumped through channels to absorb heat. The heated liquid hydrogen turns into a very hot, high-pressure gas, which is then exhausted through the nozzle. Most of these engines, in fact, run fuel-rich, to increase the percentage of hydrogen molecules. A variant of the RL-10 produced a specific impulse of 465.5 seconds. And that's about the best we can do without impractical, exotic, toxic chemicals, described in this lesson. Using a nuclear thermal rocket can double that efficiency. Nuclear thermal engines also produce a lot of thrust. This is because they can cycle propellant through the engine very quickly. This is called residence time. How long must your propellant stay in the heating part of the engine to reach its optimal temperature? The lower the residence time, the more propellant you can pump through the engine in a given period of time. The mass of propellant pumped through your engine is called the mass propellant flow. The exhaust velocity of the propellant from the nozzle, multiplied by the mass propellant flow through the engine, gives you the thrust produced. A high exhaust velocity, low mass propellant flow may not produce as much thrust as a lower exhaust velocity, high mass propellant flow, but it can provide thrust for a longer period of time. Specific impulse is a measure of how many seconds 1 kilogram of propellant could accelerate a mass of 1 kilogram to 1 g, 9.81 meters per second squared. Here we see that this time is 465.5 seconds for the RL-10 in space, 383 seconds for the methane-burning Raptor engine in space, and 304 seconds for the RP-1 burning Saturn V first-stage F-1 rocket engine once it's climbed above most of the atmosphere. That means that for each of these rocket engines, 1 kilogram of these propellants can produce 1 g of acceleration onto 1 kilogram of mass over this period of time. As you can see, none of these chemical rocket engines beat nuclear thermal. But can we beat the efficiency of the nuclear thermal rocket? It turns out that we can by using ion propulsion, specifically, for the purpose of this lesson, Hall effect thrusters. Later, if you want to learn all about the different types of ion engines, go to this lesson. The Hall effect thruster, abbreviated HET, is named after the American physicist Edwin Hall, who first discovered the Hall effect in 1879. The term Hall effect thruster was likely coined to describe the application of the Hall effect in this type of electric propulsion system. The Hall effect remains a key principle in the operation of HETs today, and the name has become widely adopted to describe this class of electric thruster. The Hall effect refers to the phenomenon where a magnetic field applied perpendicular to the flow of an electric current will cause a transverse voltage to appear across the conductor. This effect is used in HETs to generate an electric field which ionizes the propellant, and the electric field then generates a magnetic field that then accelerates the propellant ions and produces thrust. The use of the Hall effect in HETs for spacecraft was first proposed by Russian physicist V.L. Danilin in 1959, and the first successful demonstration of an HET was conducted by Yevgeny V. Shkovtsev at the Soviet Union's Central Institute of Aviation Motors in 1962. Hall thrusters were studied independently in the United States and the Soviet Union. They were first described publicly in the U.S. in the early 1960s. But the Hall thruster was first developed into an efficient propulsion device in the Soviet Union. In the U.S., scientists focused on developing gridded ion thrusters instead. The very first ion thruster to be flown in space was the SIRT-1, which stood for Space Electric Rocket Test. This ion thruster, which was developed by NASA and launched on July 20, 1964, was not a Hall thruster. It used an electrostatic ion acceleration system. The first Soviet ion thruster to fly in space was the T-5-1, which was launched aboard the Cosmos 54 spacecraft on May 30, 1965. The T-5-1 ion thruster was a gridded ion thruster and used a mercury propellant, providing a specific impulse of 1,000 seconds. But very quickly, the Soviet Union started focusing on developing more efficient ion engines, using the Hall effect. Two types of these engines were eventually developed in the Soviet Union. Thrusters with wide acceleration zones, called SPT or stationary plasma thrusters, and thrusters with narrow acceleration zones, called TAL thrusters, which stood for thruster with anode layer. The SPT design was largely the work of A.I. Morozov. The first SPT to operate in space was aboard a Soviet Meteor spacecraft and was launched December 1971. Since then, the SPT Hall effect thruster has become a well-established and widely used design, with a proven track record of successful space missions. The SPT is almost a type of gridded ion thruster, which is where the propellant is ionized and accelerated by an electric field between a series of grids. The difference is that in a gridded ion thruster, ions are pulled toward the grid by an electric field, while in this Hall effect thruster, the ions are thrown from a grid by a magnetic field. The SPT design uses a stationary plasma to produce the electric field, which allows for a compact and lightweight thruster that is well suited for use on small satellites. The TAL Hall effect thruster uses a transferred arc to ionize and accelerate the propellant. The TAL design offers some advantages over the SPT, such as higher thrust density and the ability to operate with a wider range of propellants. However, the TAL design has not yet been widely used in space missions, because it suffers from plasma field instabilities that cause fluctuations in thrust and efficiency, and erosion of the discharge channel, due to the high-energy plasma arc striking the walls. The success of the first Hall effect thrusters paved the way for the development of larger and more powerful HETs that have been used in a variety of space missions, including communication satellites, scientific probes, and deep space missions. HETs were used in NASA's Deep Space One mission, which launched in 1998 and flew to a comet and asteroid. It used Xenon for propellant, demonstrating a specific impulse of 3,100 seconds. Xenon was used because it is the heaviest of the noble gases. Unlike chemical engines, where temperature limits exhaust velocity, favoring a low atomic mass propellant, ion engines throw almost all particles at very high velocity, so improved thrust favors a heavier atomic mass particle. That is why most ion engines have used Xenon. NASA's Dawn mission used a Hall effect thruster to travel to and orbit two of the largest bodies in the asteroid belt. This HET also used Xenon as the propellant, and also provided a specific impulse of 3,100 seconds. The European Space Agency's Bepi-Colombo mission launched in 2018 and is scheduled to enter orbit around Mercury in 2025. It also uses Xenon as its propellant. But the SpaceX Starlink satellites, first launched by SpaceX, used Krypton instead. You can see my first lesson on Starlink here. SpaceX has been launching hundreds of its Starlink satellites into orbit. In fact, about half the active satellites in orbit today are owned by SpaceX. Each of these Starlink satellites use Hall effect thrusters for station keeping, which keeps the satellites where they're supposed to be in orbit, correcting for orbital perturbations like atmospheric drag. The HETs are also used for collision avoidance, very important as space gets more crowded, and for deorbiting the satellites at the end of their operational lifetime, also critical to reducing space clutter. So why did SpaceX start off using Krypton instead of Xenon? The overall efficiency of an ion engine is measured in more than just specific impulse, and depends on several factors, including the specific design of the thruster, the type of propellant used, and the operating conditions of the thruster. In general, the specific impulse of HETs using Xenon would be higher than those using Krypton or Argon, because Xenon has a higher atomic mass and ionization potential, which allows for efficient ionization and deceleration of the propellant ions. But other factors come into play. The SpaceX's Starlink Krypton-based Hall effect thrusters were designed and manufactured in-house by SpaceX, and were a key component of the company's strategy to provide high-speed internet access to users around the world. Krypton-based HETs turned out to have several advantages over traditional Xenon HETs. Krypton is less expensive than Xenon and can have a higher ionization efficiency under certain conditions, where it can be ionized more efficiently, creating the plasma that can then be accelerated to high velocities by electromagnetic fields. Overall, this can create a higher thrust-to-power ratio for Krypton-based Hall effect thrusters, making it possible for them to achieve the same level of thrust with a smaller HET, using the same power and less propellant. So the choice of propellant for any ion drive, including Hall effect thrusters, depends on various factors, such as the mission requirements, the availability and cost of the propellant, and the specific design and operating conditions of the thruster. These factors influence mass propellant flow and ionization efficiency. So SpaceX first decided to go with Krypton Hall effect thrusters. But just recently, SpaceX announced that in the new Starlink version 2 satellites, a miniaturized version of which was just delivered to space by a Falcon 9, they have switched from Krypton to Argon propellant. Why would they make this change? Krypton has a higher atomic mass than Argon, but again, that is not the only factor that determines the efficiency of a Hall effect thruster. The specific impulse of an HET also depends on the ionization energy of the propellant, the thruster design, and the operating conditions. Remember that ionization energy is not the same as ionization efficiency. Ionization energy is a fundamental property of a gas. The ionization energies for Xenon, Krypton, and Argon are 12.13, 13.99, and 15.76 electron volts respectively, while ionization efficiency is a measure of the ability of the gas to be ionized under the specific conditions that exist in a specific engine. Just like RP1 or methane might be a better choice than hydrogen for the first stage of a rocket, due to the higher fuel density and other factors, a lower mass ion propellant might be better than a higher mass one in some applications for ion engines, depending on the power available, the strength and frequency of the ionization source, and the propellant gas pressure and temperature. One reason why Argon-based HETs might be a better choice than Krypton-based HETs is that Krypton Hall effect thrusters top out at about 1,500 seconds of specific impulse, while Argon thrusters can reach an efficiency of up to 2,000 seconds. This doesn't beat the best Xenon thrusters at 3,000 seconds of specific impulse. But again, the overall ionization efficiency for Argon and the SpaceX Starlink Hall effect thruster design might be good enough to offset the difference. Power is also an issue. Ion thrusters, and indeed all spacecraft, are limited to the power available to them. This power is usually solar. The power factor helps determine the magnetic field strength, which helps determine the dimensions of the discharge channel. These factors can result in a suboptimal ionization and acceleration of the Krypton or Xenon ions, creating a lower specific impulse and efficiency when compared to an Argon propellant. So there are several reasons why SpaceX might have chosen to switch to Argon. Argon HETs also have some disadvantages. They might require higher power levels than Xenon HETs to achieve the same level of thrust, which can make them less suitable for missions where power is limited. Additionally, because argon gas is less dense than xenon gas, argon HETs require larger propellant tanks to store the same amount of propellant. But despite these limitations, argon HETs have already been used successfully on several space missions, including the European Space Agency's Gravity Field and Steady-State Ocean Circulation Explorer, which used an AHET for orbital maintenance. The new Starlink HETs are also designed to be modular and scalable, which allows SpaceX to easily adjust the number and size of HETs on each satellite, depending on the satellite's mass and mission requirements. This modularity also allows for easier replacement of HETs that may fail during a satellite's lifetime. In addition to their high performance and modularity, the Starlink HETs are also designed to be environmentally friendly. They use a water-cooled design to dissipate excess heat and reduce the risk of contamination from outgassing. They also use a non-toxic propellant and have a low impact on the space environment. To summarize why SpaceX might have shifted to Argon Hall-effect thrusters, first, Argon is less expensive than Krypton, which makes it a more cost-effective option for SpaceX's large-scale satellite constellation. By using Argon HETs, SpaceX can reduce the cost of each satellite, while still maintaining the required level of performance. Second, Argon might have a higher ionization efficiency in the SpaceX HETs, giving a higher specific impulse and higher thrust efficiency, which can lead to lower propellant consumption and longer satellite lifetimes. Third, Argon is more readily available than Krypton, which can help reduce supply chain risks and ensure a reliable source of propellant for the Starlink satellites. And finally, the switch to Argon HETs is part of SpaceX's ongoing efforts to improve the performance and reliability of their Starlink satellites by leveraging the latest technologies and materials. This represents a key technological innovation in the field of electric propulsion and will play a critical role in the success of the Starlink satellite network. It demonstrates SpaceX's commitment to developing cutting-edge technologies to advance the commercial space industry. And just perhaps, SpaceX has a further goal in mind. I actually discussed the merits of switching to argon propellant in this lesson, because while Xenon and Krypton are very rare gases, argon is not rare on Earth, nor, more importantly, is it rare on Mars. Argon makes up about 1% of the atmospheric concentration on Earth and 1.6% on Mars. So an ion engine optimized for argon, using a nuclear fission reactor for power, would be a good choice to propel ships between the Earth and Mars. Using a combination of nuclear thermal with an efficiency of 1,000 seconds specific impulse, and ion engines like the Hall-effect thruster with an efficiency of 2,000 seconds would allow a rapid departure from low Earth orbit, then a high-efficiency acceleration phase, giving us the rest of the 3,600 meters per second delta V needed to get to Mars. Then a high-thrust nuclear thermal deceleration, acquiring the 500 meters per second delta V needed for a Mars capture burn. That means a Starship could launch to low Earth orbit using the methane-fueled Raptor engines, ending up with an orbital mass of about 300 metric tons. To get from low Earth orbit to low Mars orbit with the methane engines would take about 600 metric tons of methane and oxygen propellant, requiring 4 Starship tanker launches. If instead we dock with a Mars transfer vehicle, made up of a large argon propellant tank and a nuclear reactor, with both nuclear thermal and ion thrusters, assuming a dry mass of 100 metric tons for the transfer vehicle, we would only need a propellant mass of about 60 metric tons to get the job done. This could be lifted to orbit in 1 Starship launch, dramatically reducing the number of Starship launches required to get the same number of people and mass of cargo to the New World, dramatically increasing how fast you could get a large population to their new home. Something to think about. Thanks for listening. Please don't forget we have Academy-themed gear in the Academy store, and stay safe. Ad Astra Pro Terra.